A good artist, of course, will know how to mix colors to get any color that they want, mixing different paints. And they'll understand color theory and how colors react with each other. The same is true in drawing on the computer, but it's a little more technical. And so what I'm going to try to do in this video is give you the technical background of how colors are formed and how they can be used to your advantage in Flash. Let's consider if we were in a black room and we had three people with three flashlights. One flashlight would shine red light, one would shine green, and one would shine blue. And if we converged the lights from all three onto a wall, where the three would gather together, we would have white light. Where the red and green would combine, we'd have yellow. Where the red and blue would combine, we'd have magenta. And where the green and the blue would combine, we'd have cyan. By the same token, let's consider a room where we have three lights and we have three dimmer switches attached to those lights. Those lights, just as in our previous example, would shine red, green, and blue, but we could now adjust how much light was being emitted by each bulb. So if I take this red dimmer, I can begin to fill the room with red light until I take it to its upper brightness level at a level of 255. I can do the same thing with the green. And I can begin to bring that down. So we're having just a little bit of green light, kind of a green tint within the room, and do the same thing with the blue. So on these three dimmer switches, I can begin to combine lights. I'm going to turn the red and the green all the way up, and the room will be filled with yellow light. If I combine the red and the blue, I would have magenta light. And if I combined all three full intensity, we would have white light. Now, of course, with these all off, the room is black. But I can begin to have different levels of each of these and get different colors of light. In fact, technically speaking, with 256 levels of each one of these, ranging from 0 to 255, I could get 16.7 million different shades of light if our eye could detect the technical differences. Now let's think about a computer monitor. A computer monitor is made up of millions of pixels. Each one of those pixels is representing three levels of red, green, and blue light. And each one of those red, green, and blue levels ranges from 0 to 255. So here I have a pink pixel. And if we were to look at that and look at just the color of that pixel, its setting for red is 250, green is 60, and blue is 134. Every other pixel in our monitor probably has different settings. We can represent those in a binary system of zeros and ones. If you think back to your Survey of Computer Information Systems class, we talked about how the only thing the computer really stores and recognizes is zeros and ones, high and low voltage. Those numbers of red, green, and blue can be represented by 24 bits, or 24 zeros and ones. The first 8 being the level of red, the second 8 being the level of green, and the third 8 being the level of blue. And that's called a 24-bit RGB, red, green, blue system. Let's look at how we would think in terms of those numbers. So we're used to working with decimal numbers. That's what we learned in our elementary school. We learned that a number like 172 has a certain number of ones, a number of tens, and a number of 100s. And if we could go on, we'd have thousands, 10,000s, and so forth. So in this particular case of 172, it represents a value of 1 in the hundreds place, value of 7 in the tens place, and a value of 2 in the ones place. And each one of these digits can have a value between 0 and 9. A base 10 system, thus we call it decimal. So that number 172 is 1 times 100 plus 7 times 10, which is 70, plus 2 times 1, which is 2, and we get 172. We can represent that same number in a binary system where each digit is either 0 or 1. And here is a 8-bit binary representation, and 8 bits of course is 1 byte. We have the number of 1s, number 2s, number 4s, number 8s, 16s, 32s, 64s, and 128s. So this particular number is 128 plus 32 plus 8 plus 4, and that gives us, if we convert it to decimal, a value of 172. So this is the binary representation of that number 172. When we think about 8 bits, we could have every digit being 0, and if that was the case, the value of those 8 bits converted to a decimal would be 0. And if all 8 bits were 1s, we'd have 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and we'd have a value of 255. So every byte, or every 8 bits, has a range from 0 to 255. If we're looking at that number for our pink color, that binary representation, the first 8 digits gives us a value of 250. The second 8 bits, which is green, our green value, is a value of 60. It simply is 32 plus 16 plus 8 plus 4. And then the blue is 128 plus 4 plus 2, and that gives us a value of 134. So those 8 bits combined is this color of pink. So if all of those values, the red, green, and blue, are set to 0, we get black, and if they're all set to 255, we would get white light. And then we have all those combinations in between. Now when you're working with a clients spend a lot of money doing branding, and they have specific colors that they would use. When we think about Arizona State University nearby, we know that their colors are maroon and gold. And so you might be asked to design something for them, and you would choose a maroon and gold. But you don't want to choose just any maroon or any gold. They have a guide as to which colors you should use and how you can use the logo and lettering and so forth. And in that guide it specifies that the maroon has a value of red 153, green is 0, and blue is 151. And the gold is 255 red, 179 green, and 16 blue. And you must use those colors. Well, a nice thing is in Flash, if they give you those colors, you can go in, and in Flash you can mix a color in the color panel by specifying the red, green, and blue values. And you can type those values in. It's going to give you the exact swatch color that you need out of those 16.7 million different combinations. Notice they also give you what's called a hexadecimal value. So in their communications guide, they specify for the gold a hexadecimal value of FFB310. And you could type that into Flash as well below the color swatch here, and you would get that same color. It's usually a lot easier to reference colors by these numbers, these hexadecimal numbers, rather than the decimal red, green, blue values. Let's look at how they get those. So we talked about decimal and binary. We also have hexadecimal. And this 172 in decimal values will be represented in hexadecimal as AC. In a hexadecimal number, if we had a value between 0 and 255, it would be represented by just 2 digits, the number 1s and the number 16s. Now in decimal we had a value of 0 to 9 for each digit, and binary has a value of 0 to 1 in each digit. Here we have a value of 0 to 15 for each digit. But in order to represent each digit as a single character, we have to go from 0 to 9 and then add in 6 letters. So A is 10, B is 11, C is 12, D is 13, E 14, and F 15. So in this particular case, we have A 16s, which is 10 times 16, that's 160, and C, which is 12 ones. 160 plus 12 gives us our hexadecimal equivalent of the decimal 172. So in a number like FFB310, that's hexadecimal, the first 2 digits is red, and in this case FF is 255. B3, the second 2 digits, is the green value, and this is 179, and then 10 is the blue value, and that's a value of 16. So you can see how those numbers compare to the decimal red, green, and blue system. The OX in front of this number simply tells us this is a hexadecimal value. Sometimes you also just see a pound sign or a hashtag in front of this number. The reason we do that is if I gave you the number 101010, that might look like a decimal number. Even though we can tell with the FF and the B here this is a hexadecimal, that's not always the case. So for hexadecimal, we tend to put this 0x as a notification indicator. Now there's another little aspect here to color in Flash. Where we have red, green, blue, you'll see an A. And the A stands for alpha. This is the transparency of the color. So we can have a solid color, we can also have a color that is slightly transparent. So opaque versus transparent. If this alpha is 100%, fully opaque. If it's 0, it's going to be fully transparent. If it was fully transparent, we wouldn't even see it. But here is a blue rectangle over top of a green one, and you'll see that this blue is 50% transparent, and I can see the green rectangle behind it. This is a 32-bit color system, so those extra 8 bits is the percentage of the alpha. Now rather than going from 0 to 255, we simply store it as a 0 to 100%. But it's still represented by 32 bits. In things like Photoshop or importing graphics, PNG files support 32-bit graphics. They maintain the alpha channel. A JPEG or a BMP does not. It's one advantage of PNG files over those other file formats. When you create a color in Flash, in the color panel, you can save that to your swatches. There's a little flyout menu at the top of the color panel, and in that flyout menu you can choose Add Swatch, and it will add it below the default colors in the swatches panel. So here I've taken the gold from Arizona State University, created it, and added it to my swatches. There's also a flyout on the swatch panel that you can then save this swatch collection and reload it. So you might have different swatch collections for different clients, and you don't have to keep recreating all these colors. You can simply retrieve that swatch and use it for the next project. So you might be thinking, if all the colors are made of red, green, and blue, why don't I have in my printer red, green, and blue inks? And the reason being is there are different modes of color and different ways of looking at color. When we're looking at color from a light emitting source, such as a monitor, we are using additive color. That color is hitting our eyes. When we're looking at a piece of paper that's printed, the printed page is using subtractive color, in that what is printed on that page absorbs these colors of light and reflects the opposite to our eyes. And this, for printed documents, uses a mode of cyan, magenta, and yellow rather than red, green, and blue. And you can see here that cyan is the opposite of red, yellow or magenta is the opposite of green, and yellow is the opposite of blue. So if I subtract a certain amount of red, I'm going to be left with cyan. If I subtract a certain amount of blue, I'm left with yellow. And I subtract a certain amount of green, I'm left with magenta. Now in that printing system, even though we can make black from cyan, magenta, yellow, it's kind of a muddy black. So we add in a third ink, which is black. And these are represented not from values of 0 to 255, but values from 0 to 100%. We speak of this often as a 4-color printing process. So this image here of my dog, which is made up of millions of different colors, is actually printed with 4 different inks: cyan, magenta, yellow, and black. So when you're working with a client, they may give you the values for their colors as cyan, magenta, yellow, and black, rather than red, green, blue. Now Flash is predominantly a animation system on the monitor or working with graphics on the web. We're always projecting Flash with light emission rather than printing it for the most part. So Flash does not have a color mode of working with cyan, magenta, yellow, and black. Things like Photoshop, you could use either mode. But in Flash, we're stuck with red, green, blue. There are lots of websites out there that you can go to and find where you can put in those cyan, magenta, yellow, and black values, and it will generate the red, green, blue for you, the equivalencies. And then you can plug those into Flash. Now in Flash, there's also a color mode system of hue, saturation, and brightness, and this is represented in the color panel is HSV. If I click the H radio button in the color panel Flash, I can choose a hue from the slider of the various hues. And if you think about this slider, all it is a representation of the color wheel. Basically starting here at red and going around the color wheel back to red. So I can choose a hue, and then over here in this area I can choose a saturation going from left to right, and I can choose a brightness going from top to bottom. As I change this slider to choose a hue or pick a different color with saturation and brightness of that hue, it will show me what the RGB values are for that hue that I've created, as well as the hexadecimal. These are all tied together. So if I change one value, everything else will change. I can also choose to work with this model focusing on the saturation as my slider, or brightness as my slider, in which case I can choose a hue or saturation, or if I'm doing saturation I can choose a hue or brightness level in this panel over on the left hand side. How would I use that? Well, I might draw something in Flash such as the cylinder, and I want to add some shadows and highlights. So I would add a line over here to my cylinder, and I would select the fill area then on the right hand side, and I can choose the brightness, and I can drag this brightness slider down. It's going to keep the same hue and the same saturation, but make that darker and end up with a little shadow there. By the same token, if I wanted to add a highlight, I could create two lines and it'll select the fill in between, and I would bring that brightness, in this case I would take the saturation and maybe bring it down, or I could take the brightness and bring it up, either way, but that's going to give me a nice little highlight in my cylinder. And then finally, in the color picker of Flash, I can create not just solid colors, but I can create gradients, and I can create linear gradients where it's going from left to right, or radial gradients where I'm generating outward from the center and changing colors. In the next video we'll look at how to create gradients, including multicolor gradients where I can go from green to blue to yellow to red.